Thank you. Thank you very much, Christoph. Well, it's a pleasure to be here. You're right, we've talked about this many, many times, and so it's great to actually being able to do it. I have to say that among the many reasons that I have to be grateful to Christoph is that when I went to become the deputy director of CCAM in 2014, he was the president of the CCAM Council, so it's largely his fault that I am there right now, right? So thank you for that as well. Yes, so the MaZe is a new framework and algorithm to try to simulate systems in which we have different sets of degrees of freedom, and some of these degrees of freedom are driven by others, and they have to obey specific conditions. We will see a little bit how this works in the next 3 hours or so, right? Because it's a method based on constraints, I mean, you cannot really do constraints without having something to do with Giovanni Cicotti. And so this, in fact, started with a conversation with Giovanni. More recent senior, I would say, collaborators all live in Paris, Rodolphe Villemeux, Mathieu Salan, and Benjamin Rothenberg, in between the École Normale Supérieure and Sorbonne. But really, as you know, the people who think and do the work with us, and sometimes much better than we could, are PhD students. And so this is the genealogy, the genealogical tree of my MaZe and amazing PhD students. And you may recognize here the older one of them because he's sitting there in the audience. So a lot of what I'm going to discuss today, in fact, comes from Alessandro's great work during his thesis. Anything that I say wrong, it's my fault. Anything that works, it's his doing. Now, I had to think a little bit how I wanted to tell you the story here. And so I decided to try to do this by starting to celebrate a birthday. So Italo Calvino, who is one of perhaps my favorite modern Italian writer, was born in 1923, which means that we are now celebrating his 100th birthday. But the reason why I think he is relevant for us is that he was invited in 1984 to deliver the poetry lectures for the Eliot Norton series in Harvard. And those were supposed to be 6 conferences on themes that he felt would be important to promote poetry and literature in the upcoming millennium, so the one that we are living right now. And he chose some topics that then he illustrated with a lot of beautiful examples. And he also tried to explain why he thought that these would be important values for the next millennium. So the game that I have decided to try to play today is to tell you about MaZe, trying to fit as many of these exhortations as possible in my narrative, which means that I have restructured and reorganized the way I usually give this talk. So you're playing the role of guinea pigs, and I hope you will be willing to play it with me. The reason why we started playing with this is because we wanted to study charge transfer properties in superionic conductors. So superionic conductors are materials. Here, for example, is AgI, in which you have one species in the solid state, which occupies regular lattice sites. But then you have another one, silver in this case, that can move in the lattice. And the way in which these two systems interact with one another is such that these materials can have, in certain phases, the alpha phase here for AgI, an electrical conductivity that is driven by ions, which is very, very high. For example, in the solid state, the silver ions move as fast as other ions move in liquid state. But, and there are many interesting reasons to study this type of materials, and they have been studied by many different groups. But the twist that we wanted to put on this was to look at their behavior in the presence of an external magnetic field. And in particular, the holy grail that we were after was to try to see if we could, by placing these type of systems in external magnetic field, detect ionic Hall effects, right? So we know that the Hall effect is something that happens when you place conducting electrons in a perpendicular magnetic field. They deviate because of the Lorentz force acting on them. Can you see and measure the same type of things if you look at ionic conductors? The difficulty here is that the signal is going to be much, much smaller because the mobility of the particle is inversely proportional to their mass. And so, the ions are about 2,000 times heavier than the electrons. So simulations can help understanding the mechanism and how you do about that, and how you go about this. The protagonist of our story was and is the conductivity tensor. This is the time correlation of the current components. Alpha and beta will be Cartesian components, and we need to look at all the elements of this tensor, because what happens in the absence of a magnetic field is that you have an isotropic system in which sigma xx, yy, and zz, so the components on all directions of space, are the same. Here is the black curve. But then what happens when you turn on a field, here we have a large one, as in always in simulation, is you break the isotropy of the system, and you can decrease conductivity quite substantially, and in particular in the plane that is orthogonal to the direction of the magnetic field, this can go almost to zero. So this type of devices can also be used as switches for currents with directionality. The z-axis in this case. In this case, yes. But you can play the same games in liquid molten salts, for example. And then, okay. All right, so what I am showing here are some early simulations that we did for this type of systems, in which we were modeling the interactions among the ions with empirical potentials, in which the distribution of charges around the ions were rigid. Okay, so no polarization effects in the game. And what we discovered quite soon was that for systems in particular like NaCl in the molten phase, you could not actually reproduce the finer effects, such as the ones that we were after, so the Hall effect, unless you included polarization. And this brought us to think about methods, simulation methods, to study classically polarizable force fields. Okay, and we started from the simplest one. This is called the shell model. And the general idea here is that you have your ion. Let's say this is a Coretti figure. You have here your ion. But associated to each ion, you have an additional degree of freedom, the shell, S here, that carries some charge, and it's connected to one and only one ion by a spring. And by moving around and adapting to the different configurations of your ionic systems, the motion of this charge here mimics, to some effect, the polarization of your actual system. Of course, one could try to solve this problem by looking at ab initio molecular simulations, in which you have the truest possible electronic charge density computed from the Schrödinger equation, but this becomes very expensive very rapidly, because in order to do these simulations, you need large systems and very long times for the simulation, because measuring the conductivity, which is a collective property of the system, requires a lot of statistics. And so we wanted to do it this way. Okay, now in the spirit of a Born-Oppenheimer ab initio molecular dynamics simulation, the degrees of freedom that mimic the behavior of electrons are very, very light. And so they adapt instantaneously to the position of the ions along a classical molecular dynamics trajectory in such a way that the total interaction potential, which is a function of the ionic degrees of freedom and these shell variables here, is at a minimum with respect to the position of the shells. And then you evolve the nuclei with a force that is simply minus the gradient of the potential, but computed with the shells at their minimum. Okay, so this is Born-Oppenheimer in classical molecular dynamics. This is, of course, just, but this is a broader problem, because you can think in general about an interacting system in which you have some physical degrees of freedom that now are called with capital R, and then you have some auxiliary parameters in the system. Note that here, right, if I look at what I am doing here, the only thing that evolves with a dynamical equation are the physical degrees of freedom. The shells are auxiliary variables that are simply minimized at each step along my trajectory. And so you can imagine having these being a set of parameters in a minimization problem, for example, where you want to use the dynamic of these things driven by the positions of these parameters such that they minimize some target function, in this case, a potential. Now, this is a rather common situation that you find in classical polarizable models. You find it in ab initio molecular dynamics. Born-Oppenheimer dynamics is exactly this scheme here. But you can find it also in other environments, for example, in the modeling of electrochemical cells and supercapacitors. Now, people have been trying or have been integrating evolution equations of this kind for many, many years. And there are, I would say, two families of methods. One that is a direct minimization. I really treat my S variables as external parameters. I move my ions, and then I use something like a linear or nonlinear conjugate gradient to minimize a target function, V, with respect to the S. This is Born-Oppenheimer molecular dynamics in the ab initio context. Alternatively, you can use Carparinello molecular dynamics. You can promote your parameters, your S variables, to the role of degrees of freedom in the system. You assign them a fictitious mass. You write a Lagrangian with a kinetic energy that includes that fictitious mass, and then you make that mass very, very small. And then you hope that the physics of the dynamics does for you what you want it to do. So you move the ions that are heavy and slow, and you move the S variables that are light and fast. And so because they are light and fast, they have the time. They adjust dynamically to this minimum condition. There are also some other methods out there, but all these have pros and cons. Minimization by brute force is expensive, and people typically don't converge the minimum condition with high precision, which has consequences that I will show you in a moment. And Carparinello molecular dynamics requires to follow the dynamics of these light degrees of freedom of small mass, and so you have to use a very small time step in your dynamics. And also, you are never exactly on the adiabatic surface, because you're never exactly satisfying the minimum condition. So we thought that there was room to think about it a bit more, and that's when we came up with this notion of MaZe. What is the idea here? The idea is we start from an extended Lagrangian system. So the starting point is just like Carparinello. And we write the Lagrangian for the whole system, where we have the kinetic energy of the physical degrees of freedom, the interaction potential, and our fictitious kinetic energy for these auxiliary set of variables S. But now, in addition to just the Lagrangian, we write a bunch of conditions in the form of hard constraints on the dynamics of the little S variables that correspond to the condition that we want to satisfy. So now we are moving from a Lagrangian system to a constrained Lagrangian system. We can obtain the evolution equations for this system here. And then these equations of motion will be specified in terms of some constraint forces that are just a derivative of the constraints with respect to the variables that we are interested in times Lagrange multipliers. Classical molecular dynamics, very solid, very consistent framework. Calvino number one. Now we use the notion that our auxiliary variables are light. So let's see what we can do and how far we can push this. We're going to take the evolution equations for the system. Here they are, right? And then we are simply going to observe that as far as the auxiliary variables are concerned, the acceleration of the particles is proportional to the force minus the constraint force. But this force here is 0 because that's the condition that they are always respecting thanks to the presence of the constraints. So then we can reorganize our evolution equations, and we have the evolution equations for the ions. The note are minus the gradient of the force, but they also contain the action of the constraint on the physical degrees of freedom. This is a term that we don't like because it's not there in the Born-Oppenheimer molecular dynamic. It's like the back reaction of the presence of a constraint on the auxiliary degrees of freedom on our physical degrees of freedom. Okay, so that shouldn't be there. Then we can reorganize the evolution equations for the auxiliary degrees of freedom by simply dividing by the mass left and right, and that's what we get. And now comes the crucial observation, because, okay, I want to make my auxiliary variables very light, infinitely light. I want to take the formal limits, mass goes to 0, MaZe, mass 0 dynamics, for this expression here. But I want to do that by imposing that the acceleration of my degrees of freedom stays finite. Okay. Now, in order to do that, I have to say that the Lagrange multiplier also goes to 0 together with mu. And if I impose this condition here, I assign a name, I call gamma the finite limit mu goes to 0 of this ratio here. And then I can reformulate my evolution equations in this limit. Now, if I do that, then something really nice happens, because lambda goes to 0 with mu, the term proportional to lambda in the evolution equations of the ionic degrees of freedom goes to 0. And the first line here is Born-Oppenheimer molecular dynamics for the ions. But the S variables that appear here are the ones that I obtain by solving this evolution equation here, which is I am constraining the S variables to be at a minimum. Okay, so this coupled dynamical system here automatically fulfills my constraint, and it's got a couple of advantages compared to Carparinello, for example, because you see that the small mass here has vanished. So the time step that I can use to solve this dynamical system is no longer dependent on the value of the mass of the S's. And I can do that, so then the time step goes with the nuclear time step. The problem here is that these evolution equations contain an unknown parameter, which is this gamma, which is my Lagrange multiplier. Right? It's the intensity of the force that I have to apply on the S variables to keep them on the minimum of the potential. But obtaining this gamma is something that we know thanks to yes. Nothing funny happens there because I don't even, they don't. They are, those sigma there are, the sigma here is the derivative of the potential with respect to the S variables. No masses. Okay, so let's see if I can do this. So do I know how to integrate evolution equations of the form that we had in the previous slide? Yes, thanks to Cicotti, because the way in which we do this is by propagating both the physical and the auxiliary degrees of freedom using, for example, velocity Verlet, but any algorithm will do here. And then at this point, we have an updated position for the auxiliary variables that depends parametrically on the Lagrange multiplier. But I can obtain these Lagrange multipliers by imposing that the constraint condition at the updated position is exactly satisfied. And this gives me a system of equations for gamma that I can solve by Newton-Raphson. So there is an iterative solution method for these equations, but it's a well-established procedure. Okay, so we have a formalism and we have an algorithm. Now, what are the properties of this algorithm? And here is Calvino too. There are many exact things that come out of the fact that we have formulated the dynamics using Lagrangian classical mechanics. For example, the adiabatic separation between the physical and the fictitious degree of freedom is complete because the mass of the little guys is 0. So contrary to Carparinello, I am always on the minimum surface. You can also show that if you consider the probability density that the ionic degrees of freedom follow using these dynamics, so this is the marginal with respect to the S's of the joint probability density of R and S for this system, that probability density is the exact Born-Oppenheimer probability density for the physical degrees of freedom. Furthermore, because we use shake, we can completely converge the constraint in reasonable times. I will show you this in a moment. So this is more efficient than nonlinear conjugate gradient methods, at least for the systems that we have tested it on up until now, which means that we are faster than nonlinear conjugate gradient, and we can push the constraint to exact satisfaction, which means that we have a symplectic and fully time reversible algorithm, something that in practice nonlinear conjugate gradient calculations cannot do because the convergence of the minimum condition is never precise enough. As a consequence of these things, we can go for long times because we have a very stable integration scheme. Now, there is, of course, a price to be paid for this, and that is that my constraint force here, which is the derivative of the constraint condition, sigma, is in fact a second derivative of the potential for the system that I want to integrate. So this seems to be very problematic because at least I grew up with the notion that evolution equations based on second derivatives of the potential were very, very, very bad for the scaling properties of the algorithm. But it turns out that in this particular case, or at least for the applications that we've looked at, this is not so much of a problem because the Hessian matrix is always applied to a vector. And when you have matrix vector operations, you can play tricks, typically with fast Fourier transform, that keeps the scaling under control. And I will try to show you this in a moment. Now, Calvino 3, I told you that this is a general scheme that can be applied to different systems, so a multiplicity of examples will follow now. The first one, let's look at our ionic systems with shell model, and I will start in a situation in which there is no magnetic field acting on my system. I just want to attract your attention on the fact that the interaction potential, now these are the capital R and these are the little S's in the notation that we were using. This interaction potential is a highly nonlinear function of the rho or the shell variables. So imposing the minimum of this potential with respect to rho means that we are looking at a highly nonlinear minimization problem. Okay, system of decent size, 216 particles, 216 shells. I think we've gone even higher than that, but anyways, let's stick with that. Are we accurate? So what I am showing you here are static and dynamical properties of the system, G of R's, and then velocity, autocorrelation function, and diffusion coefficients calculated using our method, which I think are the solid lines, and compared with brute force conjugate gradient calculations, one on top of the other, indistinguishable. Okay, so that's good news. We can do this for the prototypical adiabatically separated system, which is ab initio molecular dynamics, density functional based propagation. We are doing this at the moment for orbital free DFT. That's the results that I have, in which you take the energy of the ground state of a system of nuclei and electrons represented by a density, an electronic density function. You write this as a sum of different terms, and then your game is to minimize at each configuration of the nuclei along an MD trajectory, the value of this functional of the electronic density with respect to the electronic density. What you do is you take the electronic density, you expand it, for example, on a plane basis set, and then you treat the coefficients of this expansion as your auxiliary variables in the MaZe approach that I just described. And so, okay, again, if you do this, what happens is that all of a sudden the system of the size of your system explodes because you have a certain number of nuclear degrees of freedom, in this case, say 100 ions, but then you have thousands and sometimes hundreds of thousands of auxiliary variables because the expansion of the density in any basis set can require a lot of elements, right? So in this case, all of a sudden we go from 216 objects that we have to take the minimum of the potential with respect to which we have to take the minimum of the potential to say 100,000. So the size of the minimum condition that we are imposing explodes, right? But still, we're able to do this, and not just for NV dynamics, but also for Lagrangian dynamics. And the G of R is in good agreement with previous calculations. This is a system of sodium atoms, or the Borga spaceship system. And then we can compute also dynamical properties. This is a diffusion coefficient. The red line is the NVE result. And then what you have in purple and green are Lagrangian NVTs with different friction coefficients. So as we decrease the friction coefficient, we converge towards the NVE result for this. Because we have a fast way to converge the dynamics here, I can also take my ab initio molecular dynamic calculation and ask questions about ions that are not just classical particles. So I can lower the temperature of sodium. Here we go down to 25, for example, Kelvin. And I can ask, does my crystal show quantum effects, quantum nuclear effects? And there are algorithms based on path integral molecular dynamics, for example, that enable me to address this question at the price of taking each ion and turning it into a bunch of replicas of a system of the ions that I am looking at. Now, I don't want to go into the details. The message that I want to get across is to do quantum, I need to multiply the number of ionic degrees of freedom. In this case, 32 times what I had in the first instance. And again, this is something that I can do because Alessandro's way of integrating the evolution equations is in fact efficient enough and robust enough to enable to scale up the system size. And then, you can play with, for example, the G of R of this solid system. What you see here in black is the classical result. And when you crank on quantum mechanics, you find that, peaks, 0 points in peaks tend to vanish because now you have 0-point motion and tunneling effect that enable you to go from one shell of neighbors to the other, and you have broadening of the distribution due to 0-point energy motion. So these are typical results that you can get. Another type of problems that we can look at now here, this is a completely classical simulation, but we have here 2 electrodes and we have an electrolyte in the middle. And we want to look at the dynamics of this system, keeping the potential, the electric potential on these 2 electrodes at a constant value. And this can be done by decorating my electrodes that I still want to treat classically with a bunch of fictitious charges at fixed positions on a lattice here. And I have to find the correct value of these charges by imposing a minimum condition, or a condition, again, on the overall interaction potential. So now here, the Q, the capital Q, are my auxiliary set of variables, and I can play the same games that I have showed you before for very large systems getting very accurate and rapid results. So this is, boasting. Where did we start? We started by looking at polarizable, we wanted to look at polarizable models in external magnetic fields. Now, this is an interesting extension of our method because now we have the physical degrees of freedom, we have the shell variables, and we have the interaction potential, Coulomb interactions between them. But if I turn on an external magnetic field, I also have to account for the Lorentz force among my atoms, okay, that my atoms feel. Both the physical degrees of freedom and the shells. And now I want to impose as the condition for the shell variables that they feel 0 force. This is the analogous of the minimum potential condition. Here they are, right? And all of a sudden what I discover is that some of these constraints now depend on the velocities of my particles. This is intriguing for people who deal with constraints because, again, we grew up with the mantra that if a constraint is holonomic, i.e. it depends only on positions, you can use shake to solve the problem. But if you have a velocity, then no, you are in trouble, you cannot use shake. And actually, it turns out that it's simply that nobody really tried to use shake to solve a problem like this, because if the constraint is linear in the velocities, for sure, we think that this could be generalizable, but you can play games that are very, very similar to the ones that we played before to actually impose these constraints. Okay, so if you do that, then you can look at a system of NaCl in external magnetic field. Those of you who have been to the University of Rome will recognize this drawing by Bruno Tuschek. This is called the magnetic discussion. You have your evolution equations, as before, and you have evolution equations for the shell variables, where now the constraint forces are no longer the derivative of the constraint with respect to a position, but with respect to a velocity, okay? But you still have, Lagrange multipliers that you have to identify at each time step, and you can do this with a slight variation on the theme of shake. And if you do that, then you can look at static property of your system. There is a good theorem that says the G of R doesn't change in the presence or absence of a magnetic field. And this is what we see here. There are some calculations. I think the solid lines are performed with 0 external magnetic field, and the calculations with symbol instead have a magnetic field of 5.5 numbers that really have much importance here. And you can see that the 2 results lie on top of each other. This is because static properties are not affected by the presence of a magnetic field. But dynamical properties are. And so if I look at the velocity autocorrelation function for sodium and for chlorine in the presence or absence of a magnetic field, I observe different things. In particular, if I am considering a system in which there is no magnetic field, right, the off-diagonal elements, so the Vx, Vy, for example, time correlation function is going to be 0. You can prove this by symmetry. When you turn on the magnetic field, if a Hall effect is present, you will see a finite signal for that correlation function. And that's what we're seeing here. This is, say, the Vx, Vy in red, and this is the Vy, Vx in blue. And you can, in fact, prove, again, this is work that Alessandro did, you can prove that they need to be antisymmetric. And you can also then measure a diffusion constant along the XY diffusion directions in the plane. So, in the plane perpendicular to the magnetic field, and you find that it's non-zero in the presence of a magnetic field, and it's zero in the absence of a magnetic field. So we found the whole effect after about 5 years of looking for it. Calvino, again, quickness. I told you that we are efficient. Let's try to quantify that in some way. So here is an old, but always, I like this still, slide that shows what happens if you look for a non-polarizable for a polarizable classical model for sodium chloride. And if you do your minimization of the auxiliary variables using brute force methods, this is nonlinear conjugate gradient, or using MaZe. Okay. And what you see is that the number of iterations, here we are, in the schemes to get to the minimum using conjugate gradient or using MaZe is different. Not only you have more iterations that are necessary with nonlinear conjugate gradient, but you don't go downhill smoothly. You minimize, but then you grow, you minimize, then you grow, you minimize, then you grow. And that's what these poor guys are experiencing. Instead, with shake, you have a very smooth downhill path that takes you from wherever you started to the minimum. Now, wherever you fast, in few iterations, wherever you start is in fact at a point which is a relatively good guess of the solution to your minimization problem at each time step along the trajectory. And this comes from the fact that we are using as a first guess for our update of the auxiliary variables something that comes from the Lagrangian dynamics of the system. So you don't see it here, but with linear conjugate gradient, you start from or nonlinear, you start from an initial guess that is of order 1, and we start with something that is already of order, something that is of order 10, we start with something that is order 1 or smaller, in fact, smaller than that. You will see this better in a few other slides. This one here is the same type of plot, but now for the orbital free density functional calculations. And again, you see, inverted color scheme, of course, just to complicate your life, that if you use conjugate gradient, you need lots of iterations. If you use MaZe, you need much fewer iterations. And this is the initial guess, and this is the initial guess with the two different methods. Okay, and so we get for free that we start from a better initial guess. I told you that in order to use this, we have to use Hessian matrices applied to vectors. The nonlinear conjugate gradient doesn't have this problem. It only uses first derivatives. So one could ask the question, okay, you converge in less iterations, but are you faster? Because you're doing more complicated operations, right? And what we show here is that we are faster. Because the way in which we compute these second derivatives applied to the vector, again, it's not our invention, this is fast Fourier transform technology, is efficient. And because we need so many less iterations to converge, that in any case we gain. Typically a factor of 10 if you want to push both methods to very precise convergence. What happens if you don't push methods to very precise convergence? Well, here is a, a total energy plot for our orbital free calculation. And what I am showing up here in red are, in fact, 3 sets of results. 2 of them are MaZe and Born-Oppenheimer, in which I take these methods and I push both of them to numerical precision in the convergence of the minimum condition. And then you see that everything is quite nice because you have, a good conservation of energy across your whole simulation time. But then there is a third curve here, which is, okay, now I want to use MaZe, but lowering my expectations on the precision of the convergence. And so, instead of having 10 to the minus 10 as my threshold, I go to 10 to the minus 5. And what you see here is that even if I do this, my calculation remains stable in terms of energy conservation. This is one of the miracles of shake, and it comes from the fact that shake never propagates errors from one step to another. So if I'm a little wrong in the minimum at one time step, this does not affect what happens to me at the next time step. Nonlinear conjugate gradient doesn't do that. If I use a nonlinear conjugate gradient trying to be, efficient, so to have a cost of calculation, which is, say, order 10 to the minus 1, which is the same cost that I need to converge to numerical precision MaZe. So now I run to, do nonlinear conjugate gradient without using more time than what I need to converge MaZe to numerical precision. Then things become rather nasty because I can only go to a very low precision in the satisfaction of the minimum because I don't have the time to converge more. And then energy starts to drift. And you lose time reversibility, you lose all sorts of good properties that you want to sample your system correctly. So I said that this is efficient. How does it scale? In the most complicated case that we have, which is the orbital free DFT, you can prove that the best scaling that you can achieve for orbital free DFT is omega log omega, where omega is the size of the system, and that's what we have up here with MaZe. So there's nothing in this algorithm that destroys the good formal properties of the dynamics. And you can do the same also for when your magnetic field is in. Life is a little harder. You see, this is the convergence pattern when you don't have the magnetic field. 10 iterations are enough. When you turn on the magnetic field, life is a little more complicated because your initial guess is not as good as the ones that we're used to. And so you need a few more iterations. But to the best of my knowledge, no one has ever done these type of things before. And so we're playing with them and having fun. Hopefully, we can optimize them more. Or next to last Calvino, visibility. We have implemented the orbital free DFT calculations in an in-house code, but the rest we are trying to implement in open source community codes. So anything that has to do with capacitors, polarizable models, and so on and so forth is or will be implemented in this Paris developed code called Metal Walls. I didn't tell you this in the presentation, but we have a way, we already have the equations to do MaZe for not orbital free density functional theory, but for the standard density functional ab initio molecular dynamics based on constraint orbitals. And this will be implemented in Quantum Espresso and in a library called Sirius that is being developed at the Swiss Supercomputing Center. Codes are an element of visibility. You have seen the papers flashing throughout the presentation. This is the second element of visibility. Then the last point that I should discuss with you is consistency, because that's the last lecture that Calvino wanted to deliver in Harvard. And unfortunately, Calvino died before he could write this lecture or deliver the complete series in Harvard. And so I think it's appropriate that we also stop here. Thank you very much.